So in the previous lesson, we learned why it's difficult to trim a single wing or to make a single wing trim and stable. And of course, it is possible. You see flying wing designs out there, but conventionally, what's done is we use a wing tail combination, a main wing with a horizontal tail, and we see this not only in man-made aircraft but also in nature. This is often the way that nature tends to solve the problem. So we're going to look at this through a simplified analysis. Again, we're going to focus on the longitudinal characteristics of this wing-tail combination, and we're going to simplify this a bit. We're going to start off with what's called a fuselage reference line. And so this is the fuselage reference line. And we're going to assume that a lot of things lie right on this line or aligned with it. So for example, we're going to say that our free stream velocity, V infinity, is aligned with that. And that is angled relative to the horizontal by gamma. Gamma is our climb angle. So this aircraft is climbing relative to the horizontal by this angle gamma. We're going to assume that the thrust on the aircraft is aligned perfectly with V infinity. And then we're going to start with a center of gravity. And we're going to always draw that very far forward on the aircraft. And that's just to keep our coordinate system really clean here. You'll see why in just a minute. But anyway, we're going to put our center of gravity far up front. And we know that the forces acting on the center of gravity are, or it is weight. So weight acts through the center of gravity and points down towards the center of the Earth. And so now let's add our main wing and horizontal stabilizer. So I'm going to add the main wing up here, and we'll put that at kind of an angle here. So that main wing will have a mounting angle relative to this fuselage reference line of alpha sub 0 wing. Okay, so alpha naught wing. That's the mounting angle. And that main wing also sits at a distance that we're going to call L sub W. That's the distance back to the aerodynamic center of that wing, which lies on this fuselage reference line. And at the aerodynamic center, the forces that are produced by that main wing are lift, which is perpendicular to the free stream, so that's L sub W, and then drag here, which is in the direction of the free stream, so that's D sub W. And then it also produces a pitching moment that we'll call little m sub w. Now, remember, we're using little m not to mean moment, although you can think of it that way, but little m actually means pitching moment. Remember our alphabetic triad, LMN, little l meaning roll, little m meaning pitch, and little n meaning yaw. Well, little m here means pitching moment. Okay, so then let's draw the forces and moments now on the horizontal tail back here. So here's our horizontal tail, and it is mounted at an angle alpha naught h, so that's the mounting angle of the horizontal tail. And it's also placed at a distance aft of the CG. We're going to call that L sub h, and that's the location of the aerodynamic center there of the horizontal tail. Now, before we discuss the forces and moments on this tail, we have to understand one important thing, and that is that the horizontal tail is flying in what's called the downwash of the main wing. So if we go back to just wing theory, we understand from a top-down view that the aerodynamics of a main wing can be modeled by the system of vorticity, and we have downwash along the lifting line there. We have downwash coming from this sheet of vorticity back here. So everything is pushing the air down in this region, and now we've got a horizontal tail sitting back here in this region. Okay, so that horizontal tail is going to see an angle of attack that is lower than the angle of attack that the main wing sees. And so basically what happens between the main wing and the horizontal tail is that the air gets deflected downward, and so the horizontal tail is at a lower angle of attack. I'm just going to draw a vector here. So this is the velocity change along here, and we're going to say that it deflects. By the time it gets to the horizontal tail, it deflects by an angle that we're going to call epsilon sub d. So that's my downwash angle. Okay. Okay, so then the lift and drag on the horizontal are actually aligned with the local velocity vector, not with the free stream velocity vector, but with the local velocity. So that means that the lift on the horizontal is actually rotated slightly by this epsilon d value, and the drag is also rotated by epsilon d. So this is the drag on the horizontal and the lift on the horizontal, and of course, we still have a pitching moment on the horizontal, and I'm also going to draw, if I can here, a flap deflection. So this is called the elevator. This is the we're going to call that delta E. So the aft portion of the horizontal may deflect. That's called the elevator. Okay, so we now have our drawing of the major forces and moments on the simplified model of this wing-tail combination. And now we can start to look at some equations. So let's look at our trim equations, our longitudinal trim equations. Remember that says that Fx and Fz and My, excuse me, that's actually a capital My. We're just saying the moment about the y-axis are all equal to 0, right? So that's longitudinally, these are our three parameters that have to be equal to 0. The force in the x direction, force in the z direction, and moment about the y-axis all have to be 0. Okay, so we're not going to look at Fx and Fz exactly. We're going to look at those kind of rotated just a little bit. So let's actually look at the force in the thrust direction, and I suppose that could be the x direction if x is aligned with the fuselage reference line. Okay, so we're going to look at the force in the thrust direction. So thrust is acting to the left here, and then the things that are acting to the right are that's got to be equal to drag on the main wing, that's aligned with the thrust, plus the drag on the horizontal, but that's rotated, so it's actually a cosine of epsilon d multiplied by that drag on the horizontal. And then we also have lift on the horizontal that's acting in that direction, and that the component of that is the sine of epsilon d. And then we also have a weight component. Notice that weight is rotated into that the fuselage reference line direction by the sine of gamma. So plus W sine gamma. Okay, so that's our equation for balancing the forces along the direction of the fuselage reference line. And now let's look at the forces perpendicular to the fuselage reference line. So and we would call that the total lift on the aircraft, because that lift is perpendicular to V infinity. So the lift is equal to lift on the main wing plus lift on the horizontal rotated by cosine epsilon d. And then minus, we're actually going to have some drag from the horizontal times sine epsilon d. And then in the opposite direction of lift is weight. So we're going to say that's going to be equal to W times cosine of gamma, my climb angle. Okay, so that's the forces perpendicular to the fuselage reference line. And now let's look at the pitching moment about the center of gravity. We know that the pitching moment has to be equal to 0. So the pitching moment is, we have a pitching moment from the main wing, and we also have a pitching moment from the horizontal. So those can just be moved over to the center of gravity. And now we have some other forces and moments. Now notice that thrust goes right through the center of gravity, so that doesn't create a pitching moment. And also drag from the main wing goes right through the center of gravity, so that doesn't create a pitching moment. But lift from the main wing does, and that's offset by L sub W. So we've got little l sub w times capital L sub w. So little l sub w is what we're using to denote the distance or the length between the center of gravity to the aerodynamic center of the main wing. And that's going to be negative because if we have a positive L sub w or positive distance and positive lift, then that creates a nose down pitching moment. So that's why we have a negative there. Okay, and that's the same with the horizontal. So we also have minus LH times capital LH of the horizontal. That's an H. But that's rotated by cosine epsilon d. And then we're also going to have a term from the drag of the horizontal. So plus L sub H times the drag on the horizontal, and that's rotated by sine, or the component is sine epsilon d. Now, this pitching moment we know has to be equal to 0 to be trim. Okay, so these are our three equations here that say that our aircraft is trim. If all three of these equations are satisfied, then we are in a trim state. And we're going to focus on trim here for just a minute. Now, before we move on, we actually want to simplify this just a little bit more. Epsilon d is usually rather small. So the downwash angle is usually small, and so carrying around these sines and cosines is not really necessary. At least for our simplified analysis, we're going to assume that we can use a small angle approximation there. So for example, cosine epsilon d here is going to be 1, and then we can compare the magnitudes of these two terms. So lift on the horizontal compared to the drag. Usually usually lift is an order of magnitude larger than drag. So we have an order of magnitude difference here, and then cosine epsilon d went to 1. Sine epsilon d is going to just go to epsilon d from the small angle approximation. But basically we have an order of magnitude smaller component here multiplied by something very small. So we have two very small terms here multiplied together. And so we're going to say that we can neglect those relative to this lift on the horizontal. Okay, that's just part of the simplified analysis and the small angle approximation here. So this term we're actually going to drop out. We have the exact same scenario down here in the pitching moment equation. Notice that we have these same two terms here, cosine multiplied by the lift and the sine multiplied by the drag. And then both of those are multiplied by the distance of that horizontal. So we can do the same thing here. We say cosine epsilon d is 1, and that this term is small compared to the other term. And so we're just going to drop it out. And notice that I skipped over the thrust equation. We're actually not going to talk about the thrust equation really too much more, because actually all that the thrust equation would give us, if we could solve for the components in here, it would simply tell us what throttle setting we need in order to trim this equation. Okay, so this basically gives us a throttle setting to trim. And so we're not going to look at that equation anymore. We're going to be focused on these second two equations actually to make sure that both lift and pitching moment equations are satisfied. And we're going to kind of drop that throttle or the thrust equation simply because it doesn't tell us much. We'd have to know things about the propulsion system in order to basically set the throttle in order to trim this out. Okay, so let's do one more thing before we move on. We like to write equations in non-dimensional form. So let's take the lift equation and write that in a non-dimensional form. So the lift is equal to our new equation after we've applied the small angle approximation is simply L sub W plus L sub H is equal to W cosine gamma. And to non-dimensionalize this, we're going to use 1/2 rho v squared, that's the dynamic pressure. This is v infinity squared, multiplied by the area of the main wing. So the coefficients for the entire aircraft are usually are non-dimensionalized by the area of the main wing, or the properties from the main wing. So this would give us then the lift coefficient on the entire aircraft is equal to the lift coefficient on the main wing And that's simple because we're non-dimensionalizing the force on the main wing by all the parameters on the main wing, so that works out fine. Now the next term is a little bit more tricky because here we've got the lift on the horizontal and we want to non-dimensionalize it by the area of the main wing. Well, usually what we want to do instead is non-dimensionalize that by the area of the horizontal. So usually what we would have done is as we would have said, the lift on the horizontal divided by 1/2 rho v squared, where this is the velocity at the horizontal, which may be different than the free stream velocity for a couple different reasons we'll talk about here in a second. So we have 1/2 rho v squared, that's the local dynamic pressure, times the area of the horizontal. Okay, so I'm going to actually also multiply this through, so 1/2 rho v horizontal squared times the area on the horizontal, and divide by what I'm dividing the rest of this equation by. So this is 1/2 rho v infinity squared times the area of the main wing. Okay, so let's come back to this in just a minute, but let's move on to the last component here. So the last component on the right-hand side of this equation is simply the weight coefficient. We're going to call that the weight divided by 1/2 rho v squared SW is what we call the weight coefficient, and that's multiplied by the cosine of gamma, our climb angle. Okay, so I'm going to do one more thing here to simplify this equation, and that is we're going to say that this is equal to CL equals CLW plus, now this term right here we're going to call an efficiency, a tail efficiency. Okay, we're going to give it the term eta sub h. That's the tail efficiency. So this term right here, actually it's this whole thing right there. So that's the ratio of the dynamic pressures. Now I mentioned that the velocity may be different at the horizontal than it is at the main wing, and this can come from a couple different things. Of course, we have downwash that we've already talked about here, so that changes the velocity a little bit. We also have a momentum deficit because of the drag on the main wing, the velocity behind the main wing is a little bit slower. You know, the velocity that the horizontal is seeing is usually a little bit less than the velocity that the main wing is seeing from V infinity. Now, the exception to that is if we have a propeller. So if we've got some propulsion system up here that's or in front of or behind the main wing or whatever, there can be some slipstream that the horizontal stabilizer is in that is actually speeding up the flow relative to the free stream velocity. So these are tricks that that are used on different aircraft in order to trim at low airspeeds. And anyway, so we need to account for this change in general, that the horizontal may be seeing a different velocity than the free stream velocity that is seen by the main wing. And so we're just going to call this a tail efficiency factor, eta sub h. That's just the ratio of those dynamic pressures. Then we multiply by SH over SW. And then finally, this last term is simply the coefficient of lift on the horizontal, correctly non-dimensionalized. And then on the right-hand side, we have CW cosine gamma. Okay, so we've kind of worked through this a little bit laboriously, but hopefully you can recognize that this equation here now is simply a balance of forces in the direction perpendicular to our fuselage reference line. And we've written that in non-dimensional form, so it's in coefficient form. So we can do the same thing with the pitching moment equation, and I won't work through that in nearly as much detail, but if you work through and non-dimensionalize that, then what we get is a pitching moment coefficient is equal to the pitching moment coefficient on the main wing plus SH over SW, C bar H over C bar wing, eta sub H times CMH. Now, the reason this term shows up here is because we need a C bar. We need also a length to non-dimensionalize a pitching moment, and we use we traditionally use the mean chord of the main wing as that length, but of course to non-dimensionalize the pitching moment on the horizontal, we would have used the mean chord of the horizontal. So same reason we have this ratio of areas, we also have a ratio of C-bar here of the horizontal to the main wing, along with this tail efficiency that we're multiplying by the pitching moment on the horizontal, or the coefficient of pitching moment on the horizontal. And then we've got minus L sub W over C bar wing times the lift coefficient of the wing, minus L sub H over C bar W, SH over SW, eta sub H, CLH, and that whole thing has to be equal to 0. So this is our pitching moment equation in non-dimensional form. And so these two equations have to be satisfied in order for us to be trim, and we'll dig into that a little bit more in the following lessons.